Hello everybody, welcome to the first presentation of the ENGYS webinar series called Learn by Example. Today's presentation is about solving incompressible flows within HELYX. My name is Lisandro Maders, I am the General Manager of ENGYS Brazil, and I will be giving the talk today. Today's webinar goals are, first, to introduce ENGYS and some of our products and innovations, and second, to provide to you a sense of how incompressible flow cases can be easily set up within HELYX. Regarding questions, we would love to answer all of them via email after the webinar. In case you don't know ENGYS yet, ENGYS is a global provider of CFD products and services since 2009. We have phone and open phone developers since 1999, and because of such highly experienced and skilled CFD developers, we have been able to provide incredible CFD innovations to our more than 200 customers around the world. Currently, ENGYS has offices in 8 countries, and we have a well-established distributor and resellers network around the world. ENGYS was founded with the main focus of providing a CFD software that could join the benefits from both open source technology and a standard commercial software in the market. The main open source benefits I'm talking about for industry in the CFD context are full capacity of customization of the source code and free scalability. And when I say free scalability, I mean that the user can run as many simultaneous simulations and in any number of processors as the user desires, without having to buy any extra expensive HPC licenses like all other commercial CFD software in the market do. But the industry also needs efficiency and high productivity, and for that, an easy-to-use graphical user interface, high-quality technical support, and a proper documentation are needed. And this was exactly what ENGYS achieved, a CFD software which comprises all those benefits. And this resulted in the current ENGYS products, which are HELYX, our general-purpose CFD tool for enterprise applications, Elements, an advanced software suite for automotive design, with all HELYX Core and HELYX GUI components plus extra features extremely useful for the automotive industry, and the HELYX add-ons, which are a set of additional modules for HELYX and Elements for specific applications, like continuous adjoint optimization, block-coupled solver, marine hydrodynamics, and advanced multi-phase flows. So, why starting with incompressible flows? Generally, those are the starting points when learning any new CFD tool. They are the basis for more complicated problems, even though they can also be quite challenging, and it covers several engineering applications like the ones you see in the videos below. A few comments regarding the modeling of incompressible flows. Even though those are one of the simplest problems to be solved, and don't get me wrong, what I mean is that we can always add complexity, like chemical species, like heat transfer in solid and fluid regions, which is conjugate heat transfer, and compressibility of the flow. They are still fairly complex by nature. In terms of equations being solved, we can talk about a general scalar transport equation, which can be transport of momentum, mass, turbulence quantities, energy, and so on. And we still are not finished. Once the partial differential equations are chosen, we still need to solve them numerically, and it requires a set of important modeling considerations. Some of them are: first, is our problem in a steady-state regime, or is it completely unsteady? Second, what is the most appropriate turbulence modeling? Is it RANS, LES, DES? And here, as an example, we can look at the video and pictures in the right of a dry air model, which in the top you have an SUV type of vehicle whose wake behavior is strongly transient, and for those type of vehicles, modeling turbulence using DES or LES approaches is mandatory to get good convergence and accurate results. On the other hand, sedan type vehicles like the 2 pictures in the bottom sometimes are well modeled by RANS turbulence models, in which you can get good convergence and accuracy because of the weaker unsteadiness behavior of the wake. Then we need to properly set our boundary conditions, we need to choose properly our mesh resolution, to select the appropriate time step, robust numerical schemes and solver settings, and the list could continue. So those are some important modeling considerations that we need to take care when solving an incompressible isothermal flow. Okay, now let's go to the incompressible flow problem that we're going to solve using HELYX. The problem chosen was a vehicle exhaust manifold selected almost randomly in GrabCAD website, and I say almost randomly because I really like the shape of this one. And this geometry is from user Samuel Soayunan, who kindly gave permission for ENGYS to use it, so thank you. So when we are talking about exhaust manifolds, there are lots of things to be considered. For example, if we wanted to consider the real mass flow rate across such exhaust pipes, we would need to consider the volumetric efficiency curve of the engine. We would need to understand the intake process of the engine as well. We also would need to know the engine rotation and the cylinder cycles and everything to properly estimate the mass flow rates. However, all of this is of course out of the scope of this webinar, and in order to demonstrate HELYX capabilities, we will simply use a fixed mass flow rate in one of the pipes. Also, I will show quickly how the user could create a time varying table for the inlets of the pipes to represent the cylinder cycles in a transient simulation. As expected results, again, there are lots of things to evaluate. First, pressure drop across the pipes, turbulence source for acoustic noise, velocity profiles and flow patterns, trying to find areas for optimization, and so on. So let's go to the live demonstration of HELYX for this problem. So before we start, I would like to say that I am not going into all the details of our graphical user interface because I need to stick with the 20 minutes webinar. However, we will cover most of the features in the list of webinars that ENGYS is going to provide in the next weeks. So the first thing we need to choose when opening HELYX is the type of client-server connection that we want. In my case, I have both client and server in my local machine, so I'm going to select the local host. However, we have other options as well. Let's create a new case. And always remember that we don't have any license limitations on the number of processors. Let's select 12 for this case. So the first thing we need to do is to import our geometry. This particular geometry is in STL format, but we have other options as well. Also, this geometry is in millimeters, so I'm going to check this box in order to import the geometry in the correct scale. Once our geometry is imported, we can start to manipulate the surfaces. When I say manipulate the surfaces, I mean splitting it into more than one surface, or transform it, like translating, rotating, or scaling it. Or if I select more than one surface, I can join them into a group, and after they are joined, I can fuse them, for example. So let's do some of those in order to demonstrate it. I'm going to select those three parts. I'm going to join them into a group, and then I'm going to fuse them. Now all of them are in the same surface. Now let me rename the surfaces. And I'm going to put all the walls of the ducts into the same patch as well. Now we have our geometry ready, we can start meshing it. The first thing we need to do is to select the mesh algorithm. I'm not going into the details because we will have a dedicated webinar for meshing. For this webinar, let's choose the standard mesh algorithm. Next, we need to select the base mesh size. The base mesh size is basically the maximum volume cell size that we want in our mesh. All surface and volume refinements are going to be relative to this size. For this case, let's select 5 millimeters. Now, I'm going to apply to all my surfaces a surface refinement level of 1. That means 2.5 millimeters, which is half of the base mesh size. Then I'm going to select my walls, go to the Layers tab, and apply 3 layers with a Grom ratio of 1.1. We also have other options for boundary layer control. For the inlet and outlet surfaces, I want the layers to be projected onto those surfaces. So I'm going to the Layers Projection option and select Enable. Lastly, we need to select the material point location. For internal flows, the material point location should be inside our geometry. Now we can create our mesh. While the mesh is being generated, it generates a log, which contains some important information about the mesh generation. Once our mesh is ready, we can visualize it in the View tab. We can see the surface mesh, and also we can see the 3 layers being projected onto the surfaces. If we want to see the volume mesh, we can make a slice. So we go to the Slice, select Volume Mesh as source, select a plane, and click Apply. Now let's go back to the previous visualization. And since our mesh is ready, let's go to the Setup tab. In the Setup tab, the first thing we need to do is to select the options in the Solution section, which is the type of solver that we want, segregated or coupled solver. And always remember that the coupled solver is available for all customers that have acquired the HELYX coupled add-on module. If we want a steady state regime or a transient simulation, incompressible or compressible flow, if we want to solve the energy equation or not. For multiphase flows, we have different models available, and you can notice there are some of them that are grayed out. That's because those are transient models. If we select transient, they become available. And other options as well. Now let's go to the material section. Here we can define our material properties. We can create new materials, clone the existing ones, or import our own materials. Also, we have some non-Newtonian models to choose. In the Modeling tab, we can choose things like the turbulence model, buoyancy and radiation, if we were solving the energy equation, and other options depending on the type of simulation that we are going to solve. Here, we have a few options for turbulence models to choose. Let's select the standard K-epsilon model. Now, let's go to the boundary conditions. For those 2 walls, we want a no-slip type boundary condition. For this particular one, let's select a slip type boundary condition. This was an extension that I have created in order to put the outlet boundary condition a bit far from the domain of interest. For the inlet number 1, let's select an inlet type boundary condition. We have a few different options: velocity, flow rate, and pressure. Let's select flow rate in this case. Here, you can see we can apply a constant value or a time varying boundary condition, as I have mentioned in the presentation. In this option, you can enter a table with different values of a flow rate for each iteration. However, for our case, let's select a constant value. Also, we want to apply mass flow rate. For mass flow rate, we need to provide the density of our fluid. For the turbulence quantities, we have several options as well. For the other inlets, let's apply an opening type boundary condition, which is basically a total pressure boundary condition. For the outlet, let's apply an outlet type boundary condition. Let's select pressure, and let's select a fixed static pressure value. Since we are dealing with an incompressible flow, this value here is relative, so let's leave it 0. Now let's go to the numerical schemes. Here we can change things like the gradient schemes, advection schemes, flux limiters, and things like this. In the solver settings, we can change the residual control, relaxation factors, and things like this. Always remember that those two options are automatically selected by the GUI based on the options the user selected on the solution section. In the runtime control section, we need to select the number of iterations that we want to solve. For this case, let's select 300, so it runs fast for the webinar. Here, let's select the frequency that we want the GUI to write the fields into the disk. Let's simply write in the end of the run. In the field manipulation section, we can select several different post-processing utilities. If we select field process and click on the plus button, you will see the list of available post-processing utilities that we have. Let's select, for example, skin friction. Then, in the monitoring functions section, we can add, for example, a volume report monitoring function. This will report the min, maximum, and minimum values for the fields selected. We can also choose surface reports, which does the same thing as the volume report, but for a selected surface. So let's do this for the inlet number 1. And let's select pressure. In this way, we can monitor the pressure values and calculate the pressure drop across the duct number 1. Now we can initialize our flow. For velocity and pressure, let's use a potential flow solution. For the turbulence quantities, let's use a mixing random length approximation. Now we click the Initialize button. Once the fields are initialized, we can take a look in the View tab. Now we can go to the Solver tab and click Run Solver. While the solver is running, you can check the residuals through this graph. Also, you can check the surface report and volume report values as well. Now the case has run, let's go to the View tab for post-processing. The first thing we can do is to go to the last time step. Now, it's very useful to create groups to better organize our post-processing. We can change the view options as we want. Let's create some streamlines. Let's select the source of the streamlines to be the volume mesh. Let's choose the seed source to be the patch inlet number 1. And also, let's color the streamlines through the velocity magnitude. We can change the legend as we want as well. Once we are satisfied with the image, we can create scenes for later visualization. When a scene is created, I can move around. I can change anything I want. And when I click Apply to View, that scene is recovered. So, that was a quick demonstration of an incompressible flow using HELYX. Let me go back to the slides. So, a few take-home messages before we finish. We wanted to demonstrate with this webinar some of HELYX capabilities that rival other CFD commercial codes. HELYX is vastly used in the industry and has already replaced several other CFD commercial codes. Also, HELYX has an end-to-end solution for incompressible flows that includes meshing, setup, solve, and post-processing, all embedded into our graphical user interface. And the best thing is that HELYX makes use of all open source benefits. Finally, if you are interested in vehicle aerodynamic simulation, don't forget to register to our next webinar in this Thursday. Also, if you want to see the full schedule, go to our blog. For questions, you can simply reply to the email invitation for this webinar. And thank you a lot for your attention.